Quantum Consciousness. Part 2 in Quantum Consciousness. Part 1, we trace the birth of quantum physics, from the first flickers of uncertainty to the strange harmony of entanglement. Now, as we open Part 2, we step into the age of quantum information, where the universe itself begins to look less like matter and more like thought. Welcome back. You've re-entered the soft glow of Sleep Entangled, where we continue our exploration of reality's most elusive code. So find your stillness, slow your breath, and let's dive deeper, because tonight the equations whisper something new, that everything, from galaxies to dreams, might be made of meaning itself. Chapter 11, Entanglement and the Nature of Connection 1, the Invisible Thread. Every time you reach for someone's hand, share a thought, or feel a connection that seems to exist beyond words, you touch the edge of one of physics' most mysterious and profound truths: entanglement. Albert Einstein called it spukhafte Fernwirkung, spooky action at a distance. He meant it half as a joke, half as a protest. How could two particles, separated by kilometers, even light years, instantly affect each other's states? To Einstein, this was unacceptable. For decades, he and his collaborators sought ways to explain entanglement as mere illusion, a statistical trick, a hidden variable, anything but magic. But experiment after experiment has whispered otherwise. And now, more than a century later, we know the universe truly keeps its secrets in pairs. 2. When two become one. Let's imagine a single particle, perhaps a photon of light. You split it with a special crystal so that one photon becomes two, perfectly correlated twins flying apart in opposite directions. When you measure one's spin, the other's spin is instantly known, but not because information travels between them. It doesn't, it can't, not at light speed, not even close. Instead, the two are not separate things at all. They are one quantum state stretched across space. A single melody played on two instruments, each note resonating in harmony beyond time and distance. This is entanglement, the idea that separation is an illusion. 3. Bell's inequality, the test of reality. In 1964, physicist John Stuart Bell found a way to test whether entanglement was real or a clever illusion. He derived an equation, a boundary, that classical physics could never cross. If experiments broke that boundary, hidden variables would be ruled out. For years, physicists struggled to perform the test. Finally, in the 1980s, Alain Aspect and his team in Paris succeeded. Their photons defied Bell's limit. The universe, it turned out, really does cheat classical rules, and in 2022, Aspect, John Clauser, and Anton Zeilinger won the Nobel Prize for proving it beyond doubt. The verdict was in: reality is not local. Things that are connected can remain connected, no matter how far apart they drift. For the cosmic web. Now, imagine scaling that concept up. Not just two photons, but galaxies, stars, planets, all emerging from the same quantum field. Could the universe itself be entangled? Cosmologists suspect that the quantum fluctuations that seeded the Big Bang are still faintly entangled across the cosmic microwave background. When we look at the night sky, we might be gazing at echoes of correlations stretching from the dawn of time. We are, in a sense, quantum siblings, connected threads of one vast wavefunction, still humming the first note of creation. 5. Quantum teleportation, the science behind the wonder. In science fiction, teleportation means matter vanishing from one place and appearing in another. But in quantum physics, teleportation means transferring information, the quantum state of a particle, from one location to another, using entanglement as the bridge. It works like this. You have two entangled particles, A and B. You want to send the state of a third particle, C, to a distant lab. You let C interact with A, perform a joint measurement, and send the results via classical communication. Instantly, the entangled partner B adopts the state of C. Nothing physically travels, no atoms are sent, yet the essence of one particle is recreated elsewhere. It's as if the universe itself says, there is no here or there, only this. The Canary Islands experiment. In 2018, physicists tested entanglement on a cosmic scale. They used telescopes on La Palma and Tenerife, two of the Canary Islands, 143 kilometers apart. By using photons from ancient quasars to determine measurement settings, they ensured that no hidden variable could coordinate the results. The outcome? Once again, entanglement prevailed. Those photons, separated by more than a century of light travel, behaved as one. The cosmos had, in a sense, chosen correlation over chaos. 7. Entanglement in the lab and beyond. Today, entanglement isn't just a curiosity, it's a tool. Quantum engineers entangle particles to create quantum networks, secure communication systems, and quantum computers that can process vast parallel realities. At Harvard, researchers recently entangled 51 individual rubidium atoms into a quantum crystal, forming patterns of correlated light and shadow that flickered like synchronized fireflies. At IBM, superconducting circuits hold thousands of entangled qubits that compute across dimensions of probability. Every experiment, every photon, every atom whispers the same truth. Connection is the default state of the universe. 8. The human analogy. Now let's bring this down to scale. To us, have you ever thought of someone right before they texted you, or felt that eerie resonance when another person finishes your thought mid-sentence? Science can explain some of this as coincidence, cognitive bias, or social intuition. But there's another way to see it. Our brains are systems of particles, themselves entangled remnants of an ancient field. When consciousness interacts, when thoughts align, perhaps we're glimpsing the quantum foundation of empathy itself. Entanglement, then, is not just a property of particles, it is the poetry of relationship. 9. The quantum internet. The next great leap in human technology will be built entirely upon this invisible thread. The quantum internet, already tested in early prototypes, will connect computers, sensors, and satellites through entanglement. Messages will be unhackable, instant, and, in a strange sense, non-local. China's Messius satellite has already transmitted entangled photons from orbit to ground stations, over 1,200 kilometers apart. The future will see quantum repeaters linking cities, nations, and perhaps even planetary colonies. We are literally weaving a global nervous system of entanglement, a technological mirror of the cosmic web itself. 10. Fun with quantum friendship. Here's a thought experiment for the night. Imagine two best friends, separated by oceans, each with a tiny entangled photon stored in a ring around their wrist. Whenever one smiles, a signal of entangled light flickers faintly in the other's ring, invisible to the eye but known to the heart. Of course, no real photon could detect a smile, but the metaphor stands. In every moment of understanding, we are conducting a form of quantum communication. Because entanglement, at its essence, is not about particles, it's about coherence, about two systems resonating as one. 11. Experiments of the heart. A fascinating modern exploration into human quantum parallels comes from researchers at Princeton's PEAR lab, Princeton Engineering Anomalies Research. They studied whether human intention could subtly influence random number generators. After decades of trials, the results hovered just above chance, enough to intrigue, not to prove. Yet when aggregated, patterns emerged during moments of global emotional focus, major events, tragedies, celebrations. Skeptics call it coincidence, believers call it resonance. Either way, the idea persists. perhaps consciousness itself has entangling power. 12. Entanglement in biology. Quantum effects don't end at the atomic scale. They might be at play inside you right now. In photosynthesis, quantum coherence allows energy to move efficiently through chlorophyll, light finding the shortest path to life. In birds, quantum entanglement may underlie magnetoreception, helping them navigate using Earth's magnetic field. Even in the olfactory system, your sense of smell, scientists suspect quantum tunneling plays a role in distinguishing scents. So when you inhale, when you feel the sun on your skin, you're participating in quantum phenomena that blur the boundary between physics and biology. You are, in a very literal way, entangled with life itself. 13. Entanglement and time. One of the most mind-bending discoveries of the past decade is that entanglement might not only connect space, but also time. In 2013, experiments at the University of Vienna entangled particles that never coexisted. One was measured before the other was even created, yet their states were correlated. It's as if information rippled backward through the quantum field, weaving the past and future into a single, continuous fabric. What if memory and imagination, your recollection of yesterday, your dream of tomorrow, are echoes of this temporal entanglement? Maybe consciousness is how the universe keeps track of itself through time. 14. The quantum fabric of love. To speak poetically, and yet scientifically, love itself might be a macroscopic echo of quantum entanglement. When two beings form a deep emotional bond, brainwave patterns can synchronize, heart rhythms can align, and even hormone cycles fall into coherence. Studies with couples show measurable physiological mirroring during shared emotional states. No spooky physics needed, yet the pattern is eerily familiar. Separate systems becoming one, each defined by the other. So perhaps entanglement is not strange at all. Perhaps it is the rule, and individuality the exception. 15. Entanglement and death. One of the most poetic interpretations of quantum physics is that nothing ever truly disappears. Energy transforms, information persists, entanglements remain, even as particles decay and disperse. In 2021, theoretical physicist Leonard Susskind proposed that information conservation in black holes might rely entirely on entanglement. Even as matter falls beyond the event horizon, its quantum information remains encoded in the universe. If that is true, then perhaps every connection we form, every memory we leave behind, remains entangled, somewhere in the cosmic record, not lost, just diffused, not gone, just everywhere. 16. The playful universe. Let's lighten things again. If quantum entanglement is the universe's way of keeping things together, maybe it also has a sense of humour. Perhaps that sudden coincidence, that synchronicity, that perfect timing moment when reality seems to wink, is the cosmos reminding us that it's still one big system, playing with itself through us. So the next time something feels too connected to be random, you might just be hearing the laughter of entanglement echoing across space-time. 17. The participatory web. The physicist John Wheeler proposed that the universe is a participatory one, that observation brings reality into being. Entanglement, then, is the participatory thread, the handshake that keeps all participants synchronized in one vast quantum story. Every act of seeing, thinking, or feeling draws another strand into coherence. Every moment of awareness reinforces the truth that we are not observers of the universe, we are co-creators of it. 18's closing reflections. So tonight as you rest, imagine the quiet hum of entanglement all around you, in the stars overhead, in the atoms within your chest, in the minds of those you love. Each is part of the same quantum tapestry, vibrating in resonance. Distance, after all, is only a construct. And perhaps, even now, somewhere across the universe, a photon flickers in perfect harmony with your breath, reminding you that separation was never real, only beautifully disguised. Chapter 12. The Quantum Field, the Hidden Ocean of Reality. 1. Beneath the surface. Imagine for a moment the still surface of a midnight lake. No wind, no ripple, only the silent reflection of the stars above. Now imagine that beneath that surface lies an invisible ocean, infinite, restless, filled with potential. Every droplet of that unseen water carries the possibility of a wave, a sound, a spark of light. This, physicists believe, is the quantum field, the foundation from which every particle, every atom, every heartbeat emerges. The field is not empty space, it is space and the essence that fills it. 2. The field as the real reality. In classical physics, particles were tiny solid points, billiard balls colliding in predictable ways. But quantum mechanics changed that forever. We learned that what we call particles are not things at all, but excitations, brief, shimmering disturbances in a deeper medium. An electron is a wave in the electron field, a photon, a ripple in the electromagnetic field, a quark, a vibration in the quark field. All of space is filled with these fields, about 17 in total according to the Standard Model, each one overlapping, interpenetrating, and dancing through all of reality. There is no such thing as empty space. Even the vacuum teems with invisible motion. Everywhere is something. Everywhere is the field. 3. The calm that is never still. If you could somehow drain the universe of every atom, photon, and particle, you might imagine you'd be left with nothing. But quantum field theory tells us you'd still find a restless ocean of zero-point energy, a faint, eternal jitter in the vacuum itself. Even at absolute zero, when temperature vanishes and motion should cease, the field continues to hum. That hum is not noise, it's the signature of existence itself, a vibration that cannot be silenced. 4. Waves, not things. In this view, there are no objects, only events, no matter, only movement. Reality becomes less a stage filled with actors and more a piece of music, a symphony of frequencies rising and falling in intricate harmony. When you touch a solid object, you are not touching a thing. You are feeling the resistance of quantum fields, refusing to overlap. Your body, the air, the stars, all are ripples in one continuous sea. 5. Swaihu, the Higgs field, the slow dance of matter. Among these fields, one is particularly special, the Higgs field. Discovered indirectly in 2012 through the detection of the Higgs boson at CERN, it is the field that gives particles their mass. Without it, electrons would zip around at light speed, protons could never form, and atoms, let alone stars or consciousness, would never exist. As particles move through the Higgs field, they interact with it, as if moving through cosmic molasses. The stronger the interaction, the heavier the particle appears. Mass, then, is not a property you have, it's a relationship you maintain, a dialogue between motion and medium. 6. The vacuum that isn't empty. One of the most astonishing discoveries of quantum field theory is that the vacuum itself has structure. In the apparent emptiness of space, virtual particles are constantly flickering in and out of existence, brief quantum-born pairs that emerge from nothing and annihilate back into nothing. They live for less than a heartbeat of time, yet their effects can be measured. For instance, in the Casimir effect, where two metal plates placed close together experience a mysterious pull, caused by the difference in vacuum pressure between them. This is not metaphor, it's measurable physics. The void is alive. 7. A universe of fields. Each type of particle, electron, photon, neutrino, gluon, corresponds to its own field. What we perceive as matter and energy are simply different modes of vibration within these overlapping layers. It's as if the universe is composed not of marbles, but of melodies. Not bricks, but harmonics. Every interaction, every collision, every spark of light is the meeting of two waves that momentarily sing the same note. When their song ends, the waves return to silence, yet the field remains, waiting for the next verse. 8. Quantum foam and the Planck scale. Let's go deeper still, far below atoms, below quarks, below anything we can measure. At the Planck scale, about 10 to the negative 35th meters, space-time itself becomes turbulent, frothing like the crest of a wave. Physicists call this quantum foam, a chaotic sea of fluctuating geometry where distance, time, and order lose meaning. In this regime, the fabric of reality is not smooth, but granular, a living ocean constantly bubbling into new forms. From this foam, space and time themselves may emerge, like patterns forming in water as it ripples beneath the moon. 9. The field and consciousness. Here we approach a delicate intersection, where physics meets perception. If all matter and energy arise from fields, and if consciousness arises from matter, could awareness itself be a field-like phenomenon? Some physicists and philosophers, from David Bohm to Roger Penrose, have suggested that mind might not merely observe the field, it might participate in it. Perhaps thought is a subtle ripple in the same ocean, a quantum whisper rising from the vacuum that dreams of itself. 10. David Bohm's hidden wholeness. Bohm proposed a daring idea that beneath quantum randomness lies an implicate order, a hidden coherence that connects all things. In his view, what we perceive as separate particles are simply unfoldings from a deeper unified reality. Like waves rising from the same sea, each moment expresses the whole, and then folds back into it. The universe, he said, is not made of parts but of wholeness in motion, a flowing totality he called the hollow movement. To Bohm, the quantum field was not a background. It was the mind of the cosmos itself, dreaming in vibration. 11. 0-point stillness. When meditators speak of entering deep silence, of touching a space where thought dissolves, they often describe it as an infinite stillness, yet full of vitality. Physicists might describe something similar when they speak of 0-point energy, the lowest, most tranquil state the field can reach. It's not nothingness, it's pure potential. Just as a calm ocean still holds the power to form waves, the quantum field, even in perfect stillness, holds the capacity for creation. Every breath, every heartbeat, every particle that has ever existed arises from this calm and returns to it. 12. The vacuum catastrophe. Yet there is a paradox. When physicists calculate the total energy of the vacuum field, the result is mind-boggling. Something like 10 to the 120 times larger than what we observe in the universe. This mismatch, called the vacuum catastrophe, is one of the greatest unsolved problems in physics. It suggests that our understanding of the quantum field is incomplete, that perhaps the visible universe is just a delicate interference pattern floating atop an unimaginable depth of hidden energy, the ocean beneath the ocean. 13. String vibrations and field resonance. Modern theories like string theory take this one step further. They propose that even fields themselves might emerge from one deeper structure, tiny vibrating strings whose harmonics give rise to all particles and forces. In this model, everything, mass, charge, spin, is simply a note in the grand symphony of the cosmos. The quantum field becomes not just a sea of ripples, but an orchestra of dimensions. Every particle is a song, every atom a chord, every human life a verse in the cosmic score. 14. The fabric of reality. Physicists often use a phrase that sounds poetic by accident: quantum field excitations on the vacuum state. But what it really means is that reality is not made of stuff. It is made of relations, of patterns, of movement. If you've ever watched sunlight ripple through water, you've seen the essence of quantum field theory. The light isn't in the water, it is the motion itself. And you too are motion, a wave of awareness momentarily cresting in the ocean of potential. 15. The field and the self. What happens if we apply this to identity? If your body, mind, and memories are patterns in the field, then the self is not a fixed point. It's a temporary coherence. Just as a whirlpool in a river seems to exist, yet is made only of the water flowing through it, you are a whirlpool in the field of consciousness and matter, a local pattern of the infinite whole. And when you dissolve, the river continues. The pattern fades, but the water remains. There is, therefore, no death, only change of form. 16. Quantum fields and the birth of the universe. According to cosmology, the entire universe began as a fluctuation in the quantum field, a random, infinitesimal tremor that inflated into everything we see today. That initial ripple still echoes as the cosmic microwave background, a faint whisper from when the universe was just 380,000 years old. So in a way, we are the aftershock of that first vibration. Every breath you take, every word you speak, is a continuation of the universe's opening note. The field sang, and the cosmos became. 17. The quantum field as the great equalizer. One of the most humbling truths of physics is that all beings, all things, arise from the same underlying field. The starlight you see tonight, the neurons that fire as you watch it, the ink on this screen, all are manifestations of the same invisible fabric. We are not guests in the universe, we are expressions of it. Just as waves are not separate from the sea, we are not separate from the quantum field. To exist is to vibrate. To live is to resonate. Chapter 13. The Observer's Paradox, Consciousness and the Collapse of Reality. When we talk about quantum mechanics, one puzzle seems to stand taller than all others: the observer effect. It asks a question that sounds simple, but has unsettled scientists and philosophers alike for over a century. Does observation create reality? At the heart of this mystery is something called wavefunction collapse. Before we look, a quantum system, say an electron, exists in a superposition of many possible states. It doesn't have a single position or momentum. It's a cloud of probabilities spread across possibilities. But when we observe it, or when it interacts with something that acts like a measurement, that cloud suddenly collapses into a definite state. One outcome becomes real. The rest vanish as though they never existed. This collapse is not a minor detail. It is what connects the abstract world of quantum mathematics to the concrete world we live in. But what exactly triggers it? Is it the measuring device, the act of recording data, or is it consciousness itself? Let's unpack that. 1. The role of the observer. In classical physics, measurement is passive. You can weigh a stone, time a pendulum, or measure the speed of light, and those things will not care. The universe doesn't change simply because you've noticed it. Quantum mechanics is different. In experiments like the double-slit experiment, particles behave as if they know whether they're being watched. When unobserved, they act like waves, interfering with themselves, creating patterns that represent probabilities. When observed, they act like particles, picking one path, one result, one clear outcome. The act of observation seems to determine what actually is. That idea is both thrilling and deeply uncomfortable, because it suggests that consciousness, somehow, might play a role in shaping reality. Albert Einstein famously hated this implication. He called it spooky. He believed the universe should exist independently of whether anyone is looking at it. "Do you really believe," he once asked Niels Bohr, that the moon exists only when you look at it? Bohr, on the other hand, accepted the paradox. He suggested that quantum mechanics doesn't describe what is, it only describes what we can say about what is. The observer and the observed are part of the same indivisible process. This argument split physics for decades, and in some ways, it still does. 2. The measurement problem. At its core, the observer paradox is about the measurement problem. The quantum wave functions evolve smoothly, according to Schrödinger's equation, a mathematical law that predicts how probabilities change over time. But as soon as a measurement occurs, that smooth evolution abruptly stops. A single outcome is selected. The problem? The mathematics doesn't explain how or why this happens. To bridge this gap, physicists proposed interpretations, each with its own philosophical flavour. The Copenhagen interpretation, Bohr and Heisenberg, measurement causes collapse. Observation is fundamental. Reality isn't definite until it's observed. The many worlds interpretation, Everett. There is no collapse. Every possible outcome happens in a different branch of the universe. Observation just determines which branch you experience. Objective collapse theories. Wave functions collapse spontaneously when certain thresholds are met. No observer required. Relational quantum mechanics. The state of a system is always relative to another system. There's no absolute global reality. And then there's the consciousness causes collapse interpretation, the most controversial of all. It suggests that awareness itself plays a causal role in choosing outcomes. In this view, consciousness is not just observing reality, it's participating in its creation. 3. Wigner's friend. When observation becomes personal. In the 1960s, physicist Eugene Wigner proposed a thought experiment that makes this even more bizarre. Imagine his friend performing a quantum measurement inside a sealed lab. To the friend, the wave function collapses. They see a result. But to Wigner, outside the lab, his friend and the quantum system are still entangled in superposition. Who is right? Does collapse happen when the friend observes the result? Or only when Wigner learns what the friend saw? Or does it require someone else entirely? This problem scales up fast. If consciousness truly causes collapse, then every observer becomes a boundary between the possible and the actual. Each act of perception would be a creative event in the fabric of the universe. But is there evidence for that? That's where experiments come in. 4. Current experiments probing the boundary. Physicists are now designing increasingly delicate experiments to see whether observation requires consciousness. For instance, modern versions of the double-slit experiment use automated detectors instead of human eyes. The results are the same. Interference disappears once the system records which path the particle took, even if no one ever looks at the data. This suggests that consciousness is not required for wave function collapse. Interaction itself is enough. What matters is not a mind, but an exchange of information. Still, the boundary is not fully clear. Quantum systems can maintain superposition in isolation, but once they interact with their environment, air molecules, photons, even tiny vibrations, coherence is lost. This process, called decoherence, explains how the quantum world transitions into the classical one we experience. So in a sense, the observer is not a person, but the environment itself. Reality becomes definite when quantum systems entangle with so much around them that the alternatives can no longer interfere. But this doesn't end the mystery, it just moves it. If everything becomes definite through interaction, why does conscious experience seem to play such a special role in defining what is real? That's where neuroscience and quantum physics begin to overlap. 5. Consciousness as a quantum system. Some researchers, like Roger Penrose and Stuart Hameroff, argue that consciousness may itself be a quantum process. Their Au revoir theory, orchestrated objective reduction, proposes that microtubules in neurons sustain quantum states that collapse in orchestrated ways, generating moments of conscious awareness. It's a bold idea, one that tries to unify mind and matter at the most fundamental level. Critics argue that the brain is too warm, wet, and noisy for quantum coherence to survive. But new discoveries in quantum biology, such as quantum tunneling in enzymes and coherence in photosynthesis, are challenging that assumption. If biology can harness quantum effects, perhaps the brain can too. And if so, perhaps consciousness is not just affected by quantum processes, but is a quantum process. That doesn't mean you create your own reality in a mystical sense. It means that mind and matter might be two aspects of the same quantum fabric, each influencing the other through subtle lawful dynamics we're only beginning to understand. 6. Toward a unified view. Most physicists remain cautious. There's still no empirical evidence that consciousness collapses wave functions, but the question has inspired new generations of experiments, from quantum cognition models to research on how human observation might bias quantum random number generators. Meanwhile, philosophers continue to debate what the observer really means. Perhaps it's not about a conscious self, but about information, about the moment a potential becomes a fact in any system capable of registering it. In that sense, every electron, atom, or neuron might be a tiny observer, not conscious but responsive, participating in the great cosmic network of measurement that defines the world. 7. A reality shared. The observer paradox, then, is not just a scientific issue, it's a mirror for our existence. We are not detached spectators of the universe. We are embedded within it. Our observations, choices, and experiences are not just reactions to reality. They are part of how reality unfolds, whether consciousness causes collapse or simply experiences its consequences. The result is the same. To observe is to participate. So perhaps the mystery is not that the universe depends on us, but that we are expressions of its ongoing act of observation, the cosmos becoming aware of itself, one experiment, one perception, one moment at a time. Chapter 14. Quantum Reality and the Nature of Information. In the 20th century, physics underwent a transformation that went far beyond equations and laboratory results. It changed how we think about information, what it is, where it resides, and whether it might be more fundamental than matter or energy themselves. When quantum mechanics first appeared, it was treated as a theory of particles, of tiny bits of matter behaving unpredictably. But as the century unfolded, physicists began to realize that quantum theory is not really about things, it's about information. It's about what can be known, how it can be known, and how that knowledge shapes the fabric of the universe itself. Let's unpack that carefully. 1. From particles to probabilities. In classical physics, matter and energy were the bedrock of existence. You could, at least in principle, describe the position and momentum of every atom in the universe, and the future would unfold predictably from there. Quantum mechanics shattered that picture. Instead of certainty, we got probability. Instead of solid trajectories, we got wave functions, mathematical entities that describe not what is, but what could be. And when we make a measurement, we don't uncover a hidden truth. We generate a specific outcome out of many possibilities. That shift from reality as a set of facts to reality as a field of possibilities is more than philosophical. It implies that information is not just a record of what has happened, but an active participant in what becomes real. The late physicist John Archibald Wheeler, a student of Einstein, put it simply: it from bit. Every particle, every field, every space-time event arises, in the end, from binary choices, yes or no, 1 or 0, bit by bit. Reality is not built from matter, but from information. 2. What is quantum information? Let's define it clearly. A quantum bit, or qubit, is the fundamental unit of quantum information. Unlike a classical bit that must be either 0 or 1, a qubit can exist in a superposition of both until measured. When it collapses to one of the two, that single detail transforms everything. Quantum information is richer, more subtle, and far more powerful than classical information. Two qubits can be entangled, meaning their states are correlated in a way that defies classical explanation. Measure one, and the other state becomes defined, even across vast distances. This is not communication faster than light. It's a shared informational state that exists beyond space-time, a mathematical link that unites two parts of one quantum system. This informational structure is what underlies quantum computing, quantum teleportation, and even our new attempts to understand quantum gravity. So, when physicists study the quantum world, they're not just studying particles, they're studying the rules that govern how information behaves at the most fundamental level. 3. The universe as an information processor. If information is fundamental, then perhaps the universe itself is a kind of cosmic computer. That idea isn't science fiction. Physicists like Seth Lloyd and Konrad Zuse have proposed that the universe computes its own evolution. Every interaction, every quantum event, every collapse of a wave function is a processing step, a transformation of information that moves the universe forward. Think of each electron spin, each photon, as a microscopic bit of data, constantly updating the cosmic simulation. The equations of physics, then, are the rules of that computation, the software of existence. But this isn't to say we're living inside a literal computer. It's deeper than that. It's saying that information is the substrate from which space, time, energy, and matter emerge. In this view, reality doesn't store information. It is information. 4. The quantum entropy link. To understand why physicists take this idea seriously, we need to revisit a concept from thermodynamics: entropy. Entropy measures the amount of disorder in a system, or more precisely, the number of microscopic configurations that correspond to its macroscopic state. But in information theory, entropy has another meaning. It measures uncertainty. The more uncertain you are about something, the more information you gain when you learn its outcome. Quantum mechanics connects these two ideas in a profound way. The entropy of a quantum system describes not just its disorder, but its informational content. When particles become entangled, their individual entropies can change, even though the total system's entropy remains constant, a reflection of how information is shared rather than lost. This interplay between physics and information theory has become one of the most fruitful areas of modern research, especially when applied to black holes. 5. Black holes and the information paradox. Black holes are where our understanding of information faces its greatest test. When matter falls into a black hole, it seems to vanish forever. Its structure, its details, its quantum state, all lost behind the event horizon. Yet, according to quantum mechanics, information cannot be destroyed. So where does it go? This puzzle is known as the black hole information paradox. In the 1970s, Stephen Hawking discovered that black holes radiate energy, a phenomenon now called Hawking radiation. Over vast stretches of time, a black hole could theoretically evaporate completely. If that happens, what happens to the information inside? Hawking initially believed it was lost, violating the fundamental laws of quantum mechanics, but most physicists disagreed. They argued that information must somehow be preserved, encoded in the radiation, or stored on the surface of the black hole itself. That's where the holographic principle comes in. Proposed by Gerard 't Hooft and expanded by Leonard Susskind, the holographic principle suggests that all the information contained in a volume of space can be described by information encoded on its boundary. In other words, the universe may be a hologram where everything we experience in 3 dimensions is a projection from a deeper, 2-dimensional informational structure. This principle elegantly solves the black hole paradox and suggests that space-time itself emerges from information. 6. Information as the fabric of space-time. In recent decades, a new field called quantum gravity has begun to merge the physics of information with the geometry of space-time. Physicists like Juan Maldacena, Eric Verlinde, and Brian Swingle are developing models where the fabric of the universe literally arises from the entanglement of quantum information. Imagine space-time as a vast network, a cosmic web where each node represents a quantum system and each connection represents entanglement. The more entangled the systems, the more connected space becomes. Distance, geometry, even gravity itself could be emergent phenomena arising from patterns of information. This means that space and time are not fundamental. They are appearances that arise from a deeper informational order. When information changes, the shape of space-time itself changes. In this framework, a black hole isn't just a collapsed star, it's an extreme concentration of quantum information, encoded at its surface like data on a cosmic hard drive. The universe, then, may be both physical and informational, both real and digital, a self-generating tapestry woven from threads of entanglement. 7. Experiments at the edge of understanding. These ideas might sound abstract, but they're now being tested in laboratories. Physicists have begun performing quantum simulations, creating tiny analogues of space-time using entangled atoms and photons. In 2022, a team at Caltech even simulated a miniature version of a wormhole, showing that entangled quantum systems can behave like connected regions of space. Meanwhile, quantum computers are emerging as tools not just for computation, but for exploring fundamental physics. They can model systems too complex for classical computers to handle, including aspects of quantum gravity and black hole evaporation. In quantum communication experiments, scientists have already demonstrated quantum teleportation, the transfer of information between particles without any physical connection. While it's not beaming matter like in science fiction, it's an astonishing example of how information itself can move through the quantum realm. Each of these experiments adds weight to the idea that information is not a metaphor. It's the foundation of everything. 8. The philosophical implications. If reality is made of information, what does that mean for us? First, it reframes the question of consciousness. Our thoughts, perceptions, and memories are patterns of information processing within the brain. If the universe itself processes information, then consciousness might not be an anomaly. It might be a natural expression of the universe's own informational dynamics. Second, it challenges our idea of reality. If everything, atoms, galaxies, emotions, light, can be described as information, then perhaps the distinction between physical and mental, between matter and meaning, is not as clear as we once thought. Third, it raises a subtle but profound question. If reality is informational, who or what is reading the code? This isn't a call for mysticism. It's an acknowledgement that we, as observers, are part of the same informational system we're trying to describe. Every measurement, every act of observation adds new information to the universe, shaping its ongoing evolution. The cosmos, in that sense, may be a self-aware network, not because it has a mind, but because it contains within it the capacity for self-reflection. Through us, it studies itself. 9. From uncertainty to understanding. We began this journey centuries ago with the belief that physics would one day describe everything with certainty. What we've learned instead is that uncertainty is not a flaw, it's the canvas upon which reality is painted. Quantum information theory doesn't eliminate mystery, it quantifies it. It shows that even the unknown follows patterns, that uncertainty has structure, and that the act of asking questions, of observing, is woven into the universe's own architecture. In this light, physics becomes not just a search for facts, but a dialogue between information and awareness, order and randomness, the known and the possible. 10. The Great Informational Tapestry. Imagine zooming out, far beyond the Earth, beyond the galaxies, into the vast silent expanse of the cosmos. Now imagine that what connects it all isn't empty space but a sea of relationships, each encoded in quantum information. Every star, every atom, every heartbeat, every photon is part of one universal computation, a continuous exchange of possibilities crystallizing into reality. We are not observers standing outside that system. We are participants within it, living nodes in the web of information that defines existence. Perhaps that's the true lesson of quantum physics. Reality is not a collection of objects, but a network of information constantly unfolding, collapsing, and recombining. And as long as there are observers, systems that gather, process, and share information, the universe will continue to compute itself into being. Chapter 14: Quantum Reality and the Nature of Information. In the 20th century, physics underwent a transformation that went far beyond equations and laboratory results. It changed how we think about information, what it is, where it resides, and whether it might be more fundamental than matter or energy themselves. When quantum mechanics first appeared, it was treated as a theory of particles, of tiny bits of matter behaving unpredictably. But as the century unfolded, physicists began to realize that quantum theory is not really about things, it's about information. It's about what can be known, how it can be known, and how that knowledge shapes the fabric of the universe itself. 1. From particles to probabilities, in classical physics, matter and energy were the bedrock of existence. You could, at least in principle, describe the position and momentum of every atom in the universe, and the future would unfold predictably from there. Quantum mechanics shattered that picture. Instead of certainty, we got probability. Instead of solid trajectories, we got wave functions, mathematical entities that describe not what is, but what could be. And when we make a measurement, we don't uncover a hidden truth. We generate a specific outcome out of many possibilities. That shift from reality as a set of facts to reality as a field of possibilities is more than philosophical. It implies that information is not just a record of what has happened, but an active participant in what becomes real. The late physicist John Archibald Wheeler, a student of Einstein, put it simply: it from bit. Every particle, every field, every space-time event arises, in the end, from binary choices. Yes or no, 1 or 0, bit by bit. Reality is not built from matter, but from information. 2. What is quantum information? Let's define it clearly. A quantum bit, or qubit, is the fundamental unit of quantum information. Unlike a classical bit that must be either 0 or 1, a qubit can exist in a superposition of both, until measured when it collapses to one of the two. That single detail transforms everything. Quantum information is richer, more subtle, and far more powerful than classical information. Two qubits can be entangled, meaning their states are correlated in a way that defies classical explanation. Measure one, and the other's state becomes defined, even across vast distances. This is not communication faster than light. It's a shared informational state that exists beyond space-time, a mathematical link that unites two parts of one quantum system. This informational structure is what underlies quantum computing, quantum teleportation, and even our new attempts to understand quantum gravity. So, when physicists study the quantum world, they're not just studying particles, they're studying the rules that govern how information behaves at the most fundamental level. 3. The universe as an information processor. If information is fundamental, then perhaps the universe itself is a kind of cosmic computer. That idea isn't science fiction. Physicists like Seth Lloyd and Konrad Zuse have proposed that the universe computes its own evolution. Every interaction, every quantum event, every collapse of a wave function is a processing step, a transformation of information that moves the universe forward. Think of each electron spin, each photon, as a microscopic bit of data, constantly updating the cosmic simulation. The equations of physics, then, are the rules of that computation, the software of existence. But this isn't to say we're living inside a literal computer. It's deeper than that. It's saying that information is the substrate from which space, time, energy, and matter emerge. In this view, reality doesn't store information, it is information. 4. The quantum entropy link. To understand why physicists take this idea seriously, we need to revisit a concept from thermodynamics: entropy. Entropy measures the amount of disorder in a system, or more precisely, the number of microscopic configurations that correspond to its macroscopic state. But in information theory, entropy has another meaning. It measures uncertainty. The more uncertain you are about something, the more information you gain when you learn its outcome. Quantum mechanics connects these two ideas in a profound way. The entropy of a quantum system describes not just its disorder, but its informational content. When particles become entangled, their individual entropies can change, even though the total system's entropy remains constant, a reflection of how information is shared rather than lost. This interplay between physics and information theory has become one of the most fruitful areas of modern research, especially when applied to black holes. 5. Black holes and the information paradox. Black holes are where our understanding of information faces its greatest test. When matter falls into a black hole, it seems to vanish forever. Its structure, its details, its quantum state, all lost behind the event horizon. Yet according to quantum mechanics, information cannot be destroyed. So where does it go? This puzzle is known as the black hole information paradox. In the 1970s, Stephen Hawking discovered that black holes radiate energy, a phenomenon now called Hawking radiation. Over vast stretches of time, a black hole could theoretically evaporate completely. If that happens, what happens to the information inside? Hawking initially believed it was lost, violating the fundamental laws of quantum mechanics. But most physicists disagreed. They argued that information must somehow be preserved, encoded in the radiation, or stored on the surface of the black hole itself. That's where the holographic principle comes in. Proposed by Gerard 't Hooft and expanded by Leonard Susskind, the holographic principle suggests that all the information contained in a volume of space can be described by information encoded on its boundary. In other words, the universe may be a hologram, where everything we experience in 3 dimensions is a projection from a deeper, 2-dimensional informational structure. This principle elegantly solves the black hole paradox and suggests that space-time itself emerges from information. 6. Information as the fabric of space-time. In recent decades, a new field called quantum gravity has begun to merge the physics of information with the geometry of space-time. Physicists like Juan Maldacena, Eric Verlinde, and Brian Swingle are developing models where the fabric of the universe literally arises from the entanglement of quantum information. Imagine space-time as a vast network, a cosmic web where each node represents a quantum system and each connection represents entanglement. The more entangled the systems, the more connected space becomes. Distance, geometry, even gravity itself could be emergent phenomena arising from patterns of information. This means that space and time are not fundamental. They are appearances that arise from a deeper informational order. When information changes, the shape of space-time itself changes. In this framework, a black hole isn't just a collapsed star, it's an extreme concentration of quantum information, encoded at its surface like data on a cosmic hard drive. The universe, then, may be both physical and informational, both real and digital, a self-generating tapestry woven from threads of entanglement. 7. Experiments at the edge of understanding. These ideas might sound abstract, but they're now being tested in laboratories. Physicists have begun performing quantum simulations, creating tiny analogues of space-time using entangled atoms and photons. In 2022, a team at Caltech even simulated a miniature version of a wormhole, showing that entangled quantum systems can behave like connected regions of space. Meanwhile, quantum computers are emerging as tools not just for computation, but for exploring fundamental physics. They can model systems too complex for classical computers to handle, including aspects of quantum gravity and black hole evaporation. In quantum communication experiments, scientists have already demonstrated quantum teleportation, the transfer of information between particles without any physical connection. While it's not beaming matter like in science fiction, it's an astonishing example of how information itself can move through the quantum realm. Each of these experiments adds weight to the idea that information is not a metaphor, it's the foundation of everything. 8. The philosophical implications. If reality is made of information, what does that mean for us? First, it reframes the question of consciousness. Our thoughts, perceptions, and memories are patterns of information processing within the brain. If the universe itself processes information, then consciousness might not be an anomaly. It might be a natural expression of the universe's own informational dynamics. Second, it challenges our idea of reality. If everything, atoms, galaxies, emotions, light, can be described as information, then perhaps the distinction between physical and mental, between matter and meaning, is not as clear as we once thought. Third, it raises a subtle but profound question. If reality is informational, who or what is reading the code? This isn't a call for mysticism, it's an acknowledgement that we, as observers, are part of the same informational system we're trying to describe. Every measurement, every act of observation adds new information to the universe, shaping its ongoing evolution. The cosmos, in that sense, may be a self-aware network, not because it has a mind, but because it contains within it the capacity for self-reflection. Through us, it studies itself. 9. From uncertainty to understanding. We began this journey centuries ago with the belief that physics would one day describe everything with certainty. What we've learned instead is that uncertainty is not a flaw, it's the canvas upon which reality is painted. Quantum information theory doesn't eliminate mystery, it quantifies it. It shows that even the unknown follows patterns, that uncertainty has structure, and that the act of asking questions, of observing, is woven into the universe's own architecture. In this light, physics becomes not just a search for facts, but a dialogue between information and awareness, order and randomness, the known and the possible. 10. The great informational tapestry. Imagine zooming out, far beyond the Earth, beyond the galaxies into the vast, silent expanse of the cosmos. Now imagine that what connects it all isn't empty space, but a sea of relationships, each encoded in quantum information. Every star, every atom, every heartbeat, every photon is part of one universal computation. A continuous exchange of possibilities, crystallizing into reality. We are not observers standing outside that system. We are participants within it, living nodes in the web of information that defines existence. Perhaps that's the true lesson of quantum physics. Reality is not a collection of objects, but a network of information constantly unfolding, collapsing, and recombining. And as long as there are observers, systems that gather, process, and share information, the universe will continue to compute itself into being. Chapter 15. Quantum Consciousness Between Physics and Mind. For centuries, consciousness stood apart from physics. It was the province of philosophers, poets, and psychologists, something to be felt and described, not measured or modelled. Physics, on the other hand, dealt with what could be weighed, counted, and calculated. Yet as the quantum revolution reshaped our understanding of the physical world, the boundaries began to blur. When observation itself became a crucial part of the theory, when the act of measurement appeared to influence the outcome, scientists were forced to ask an unsettling question. Could consciousness be woven into the fabric of quantum reality? 1. The measurement problem, where consciousness entered physics. Let's start from the heart of quantum mechanics, the measurement problem. A quantum system can exist in many possible states simultaneously. An electron can be in multiple places at once. A photon can travel several paths at once. This superposition persists until the system is measured. At that moment, the wave function collapses, and only one outcome becomes real. But what exactly counts as a measurement? Is it the interaction with a detector, the recording of a result, or is it the moment a conscious observer becomes aware of the delta? This ambiguity has haunted quantum theory since its birth. Physicists like Niels Bohr argued that quantum mechanics only describes what we can say about nature, not nature itself. But John von Neumann went further. He mathematically showed that the boundary between the measuring apparatus and the observer can be pushed arbitrarily far, even to include the entire physical world. And yet, somewhere, a conscious observer must appear to collapse the wave function. This led to what's known as the von Neumann-Wigner interpretation, the idea that consciousness plays a direct role in determining physical reality. To many physicists, that sounded like mysticism invading science. But others saw it as a sign that our theory of the universe was incomplete, that we might be missing something essential about the role of mind in the structure of the cosmos. 2. Schrödinger, Wigner, and the question of mind. Even Erwin Schrödinger, whose famous equation describes the evolution of quantum systems, wrestled with this problem. He created his now famous thought experiment, the cat that is both alive and dead, to highlight how absurd it seems to apply quantum principles to everyday life. The cat, sealed in its box, remains in a superposition until observed. But who exactly counts as the observer? The cat itself? The scientist opening the box? The universe at large? Eugene Wigner, a Nobel laureate, took the question seriously. He argued that consciousness is not a byproduct of physics. It's a fundamental component of the universe, one that might be necessary for the collapse of the wave function. He wrote, "It was not possible to formulate the laws of quantum mechanics in a fully consistent way without reference to consciousness." For Wigner, the universe doesn't merely exist in a fixed, objective state. It's participatory. Reality crystallizes only when observed by a conscious mind. While this view has fallen out of mainstream favour, it remains one of the most provocative interpretations in modern physics. 3. Decoherence and the mind-free solution. Most contemporary physicists prefer to explain measurement without invoking consciousness. The leading approach is decoherence theory, developed by H. Dieter Say and expanded by Wojciech Zurek in the 1970s and 1980s. According to decoherence, quantum superpositions don't vanish because of consciousness. They vanish because of environmental interaction. When a quantum system interacts with its surroundings, even a few stray photons, the delicate coherence of its wave function is destroyed. The system becomes entangled with its environment, effectively collapsing into one of many possible outcomes. In this view, measurement doesn't require a mind, only complexity. The observer is just another physical system, part of a vast chain of interactions. Yet even this explanation doesn't eliminate the deep question. If reality is just information, as we saw in the previous chapter, then what does it mean for that information to be known? That word, known, carries a flavour of awareness. It suggests that the universe contains not only data, but also meaning. 4. Quantum biology, consciousness in the living world. While physicists debated abstract principles, biologists began uncovering something surprising. Quantum effects might be at work inside living systems. In photosynthesis, for instance, light-harvesting molecules use quantum coherence to transfer energy with almost perfect efficiency. In birds, entangled particles in their eyes seem to help them navigate Earth's magnetic field. Even the sense of smell may involve quantum tunneling, where electrons leap through barriers in molecular receptors. These findings gave birth to a new field, quantum biology, showing that life itself might exploit quantum phenomena to function optimally. If quantum effects can operate in such noisy, warm environments as a cell, could the brain, the most complex structure we know, also use them? That's the question behind one of the most intriguing theories of consciousness ever proposed. 5. The Penrose-Hameroff model, orchestrated objective reduction. In the 1990s, Sir Roger Penrose, a mathematical physicist, and Stuart Hameroff, an anesthesiologist, proposed the orchestrated objective reduction, OR theory. Penrose argued that consciousness cannot be explained by computation alone. Something non-algorithmic, something tied to the fundamental structure of space-time, must be involved. He proposed that quantum collapses, objective reductions of the wavefunction, could occur inside the brain's microtubules, tiny cylindrical structures within neurons. Hameroff added the biological details. Microtubules might support coherent quantum states that orchestrate neural firing patterns, giving rise to moments of conscious experience. In this model, consciousness arises not just from the brain, but from quantum events embedded in the geometry of the universe itself. Each collapse of a quantum state would correspond to a discrete moment of awareness. Though controversial and difficult to test, OR remains one of the few scientific models attempting to bridge quantum physics and subjective experience. And interestingly, research in anesthesia, Hameroff's field, supports the idea that microtubules might indeed play a role in consciousness, since anesthetics act directly on them. 6. Quantum coherence in the brain, evidence and debate. Skeptics argue that the brain is too warm and wet for quantum coherence to survive. Quantum states are fragile, easily destroyed by thermal noise. Yet in recent years, experiments have shown surprising results. At the University of California, researchers using advanced imaging found that quantum-like coherence may persist in certain neural microstructures for measurable time spans. Meanwhile, work in quantum neurobiology suggests that ion channels, neurotransmitter molecules, and even DNA might exhibit quantum tunneling effects relevant to neural processing. None of this proves that consciousness is quantum mechanical, but it keeps the door open. If the brain does harness quantum effects, it could explain some of the mysterious features of consciousness, such as unity, non-local awareness, and the sense of flowing time. In quantum theory, after all, information can be non-local, spread across entangled systems that behave as one. Perhaps our sense of unified awareness is, in some way, a macroscopic reflection of quantum integration occurring at the microscopic level. 7. Consciousness as an emergent quantum field. Another line of thinking flips the idea around. Instead of asking whether consciousness uses quantum mechanics, it asks whether consciousness itself is a quantum field, a fundamental property of the universe, like gravity or electromagnetism. This approach is sometimes called pan-proto-psychism or quantum panpsychism. The view that consciousness is not created by matter, but is a basic feature of reality that matter can express in complex ways. In this model, every quantum event has a tiny proto-experience. When systems become highly organized, as in a brain, these experiences integrate into what we recognize as consciousness. This isn't to say that rocks or electrons have thoughts. Rather, it's saying that the potential for awareness is built into the fabric of quantum information itself. It's a natural extension of the information is reality framework we explored earlier. If information is the foundation of the universe, and consciousness is what interprets or experiences information, then they may be two sides of the same phenomenon. 8. Experiments and models at the frontier. Although much of this remains theoretical, new technologies are beginning to probe the boundaries between mind and quantum matter. In Japan, neuroscientists are experimenting with quantum sensors to detect ultra-weak magnetic fields produced by brain activity with a sensitivity approaching the quantum limit. At MIT and Oxford, quantum computing techniques are being used to simulate neural dynamics, exploring how entanglement might enhance computation. And in the Netherlands, physicists have proposed experiments where entangled photons could, in principle, be influenced by human intention, a controversial but testable idea. Even if such results remain inconclusive, they signal a profound shift. Science is beginning to treat consciousness not as a mystery beyond physics, but as part of the same continuum that includes atoms, fields, and space-time. 9. The double role of the observer. There's another subtler way that quantum physics and consciousness intersect, not through brain microtubules or quantum fields, but through information itself. In every quantum experiment, the observer plays two roles. First, as a participant, a physical system that interacts with the world. Second, as a knower, a mind that interprets and assigns meaning to the result. No equation in physics fully describes that second step. The mathematics tells us what happens when a system is measured, but not what it means for an outcome to be experienced. That bridge from objective event to subjective awareness remains unbuilt, yet without it, physics is incomplete. For all our progress, we still don't know how the feeling of being, the raw sense of existence, fits into the mathematical structure of the universe. Quantum theory reminds us that the act of observation isn't trivial. It's not a passive glance into an independent world. It's an interaction, and possibly a co-creation, between mind and matter. 10. Toward a unified understanding. So where does all this leave us? We have three main possibilities. 1. Consciousness causes collapse. The mind plays a direct role in shaping physical reality, as in Wigner's interpretation. 2. Collapse causes consciousness. Quantum events within the brain generate awareness, as in Oshua. 3. Consciousness and physics are two sides of one informational coin, both arising from a deeper, unified substrate. Each possibility challenges the way we've been trained to think, separating subject from object, mind from matter, observer from observed. If we take quantum information seriously, those divisions may be illusions. Reality might be a single seamless process, a network of interactions that, at one scale, appears as physical law, and at another as conscious experience. In that sense, when we study quantum mechanics, we're also studying ourselves, not metaphorically, but literally, because the same principles that govern subatomic particles govern the informational processes that make thought and perception possible. 11. Consciousness as the universe. Knowing itself. Carl Sagan once said, "We are a way for the cosmos to know itself." Quantum physics gives that statement a new depth. If the universe is made of information, then consciousness is not separate from it. It's the part of the universe that reflects, questions, and understands, the part that turns data into meaning. Every act of awareness, from the firing of neurons to the contemplation of galaxies, adds another thread to the cosmic web of information. Through consciousness, the universe observes its own equations, measures its own states, and becomes aware of its own being. This isn't mysticism, it's a kind of scientific humility. It's recognizing that, in studying reality, we are not outside of it, we are one of its phenomena. 12. The road ahead. The study of quantum consciousness is still young, often controversial, and sometimes speculative, but it's also one of the most exciting frontiers of science. It invites collaboration between physics, neuroscience, philosophy, and computer science. It asks questions that reach beyond technology and touch the heart of what it means to exist. As quantum technologies continue to evolve, as we build computers that harness superposition, sensors that touch the quantum limit, and instruments sensitive to the faintest signals of entanglement, we may one day find that the observer effect is not just a feature of experiments, but a window into consciousness itself. 13. Closing reflections. Perhaps the divide between physics and consciousness was never real. Perhaps they've always been part of the same story. Two expressions of one principle: the unfolding of information into awareness. Quantum theory gave us uncertainty, but it also gave us connection, entanglement, coherence, and the realization that reality is participatory. Maybe consciousness isn't something that emerges from the universe. Maybe it's the universe emerging from itself, seen through the eyes of experience. And maybe, when we close our eyes and think, when we observe our own thoughts, the same laws that guide particles in superposition are quietly at work, guiding the dance between mind and matter. Chapter 16. Quantum time, why the future might already exist. Time is one of the most familiar things in our lives. We wake up, eat breakfast, watch the day unfold, and eventually drift into sleep. It seems to flow in one direction, from past to future, from what has happened to what will happen. But when you look at time through the lens of quantum physics, that comforting flow begins to blur. Moments may not be neatly arranged like pearls on a string. Instead, they could be part of a vast, interconnected web, one in which past, present, and future are woven together in ways we're only beginning to understand. 1. The arrow of time, a classical illusion. In classical physics, time behaves like a one-way street. Entropy, the measure of disorder, always increases, and that gives time its direction. You can watch an egg break, but never see it unbreak. Heat spreads, but never spontaneously gathers. This arrow of time defines our experience of reality, yet if you write down the equations of motion that govern atoms or galaxies, they don't distinguish between past and future. They work equally well in either direction. The fundamental laws of physics are time symmetric. So where exactly does the arrow of time come from? Why does the universe seem to prefer one direction? Some physicists argue that it's a statistical illusion, a product of initial conditions set at the Big Bang. Others suspect that the arrow of time might emerge from something deeper, perhaps from the quantum structure of information itself. 2. Quantum time reversal. When effects precede causes. In the quantum world, the line between past and future becomes even more slippery. Take the delayed choice experiment, proposed by John Archibald Wheeler. It's a variation of the double-slit experiment, where particles like photons seem to act like both waves and particles, depending on how you measure them. In Wheeler's version, you decide how to measure the photon after it has already entered the experimental setup, even after it could have gone through one slit or both. Incredibly, the outcome seems to retroactively determine what the photon did in the past. Did it travel through both slits as a wave, or one slit as a particle? The answer depends on a decision made in the present, as though the photon knew what would be asked of it later. This is one of those moments in physics where our intuitive understanding of time simply collapses. Cause and effect seem entangled. The future appears to influence the past. Physicists call this quantum retrocausality, and while it remains controversial, it is mathematically consistent with the equations of quantum mechanics. 3. The transactional interpretation. Handshakes across time. To make sense of such paradoxes, physicist John Cramer proposed the transactional interpretation of quantum mechanics in the 1980s. In this model, quantum events are like conversations between the past and the future. When a photon is emitted, it sends a wave forward in time, and the detector sends a confirmation wave backward in time. Only when the two waves meet, a handshake across time, does the event actually occur. This explanation elegantly resolves the strangeness of quantum experiments without invoking observers or collapsing wave functions. Instead, reality is formed through transactions that span both directions of time. In this sense, every moment, every quantum event is part of a dialogue between what was and what will be. The present is simply where those conversations intersect. 4th, entanglement and temporal non-locality. Most people know about spatial entanglement, where two particles remain connected across space, influencing each other instantaneously, no matter the distance. But there's also temporal entanglement, where quantum correlations extend across time. In experiments at the University of Vienna and the University of Queensland, researchers have shown that particles can be entangled not only across space, but also between different moments in time. Measure one particle today, and the outcome can be statistically linked to a particle that no longer exists, a particle measured yesterday. This suggests that quantum information doesn't just span across distances, it spans across time. The universe doesn't neatly divide events into before and after. Instead, it may operate as a single unified system, where all events coexist in a shared quantum state. 5. The block universe, time as a dimension, not a flow. Einstein's theory of relativity deepened this mystery even further. According to relativity, time is a dimension of space-time, not something that flows, but something that is. All moments, past, present, and future, coexist within the four-dimensional structure of the universe. This concept is known as the block universe. From this perspective, your birth, your present moment, and your future are all equally real, just located at different coordinates in space-time. We experience the passage of time not because it moves, but because our consciousness moves through it. Like a spotlight scanning across a film reel, Einstein himself expressed this idea in a letter after his friend Michel Besseau passed away. For us believing physicists, the distinction between past, present, and future is only a stubbornly persistent illusion. If that's true, then the future isn't something that happens. It's something that already exists, waiting for us to experience it. 6. Quantum indeterminacy versus the block universe. But if all moments already exist, how can we have free will? And how do we reconcile that with quantum indeterminacy, the apparent randomness of quantum outcomes? One interpretation is that quantum mechanics fills in the details of the block universe as we go. The structure of time might be fixed, but the content, the precise outcomes of quantum events, unfolds through probability. Imagine a book that's already written but not yet read. All the chapters exist, but their meaning only emerges when consciousness moves through them, page by page. This analogy helps unify the deterministic geometry of relativity with the probabilistic nature of quantum mechanics. A step toward what some theorists call quantum causal order. 7. The quantum switch, when before and after blur. Recent experiments in quantum information theory have gone a step further, showing that even the order of events can become indefinite. In 2019, researchers demonstrated a device called a quantum switch, where two operations, say A and B, are applied to a quantum system, but the order in which they occur is not fixed. Sometimes A happens before B, sometimes B before A, and sometimes both orders exist simultaneously. This phenomenon, called indefinite causal order, has no parallel in classical physics. It suggests that, at the quantum level, the sequence of time itself can be in superposition. When applied to information theory, this principle allows for faster and more efficient quantum computations, but philosophically, it's even more radical. It means that our most basic assumption, that cause precedes effect, is not universally true. 8. Time loops and quantum consistency. If the future can influence the past, could we have time loops? Self-consistent cycles in which information or events feed back into themselves? Physicist David Deutsch explored this idea using the framework of quantum computation. He proposed that quantum mechanics can accommodate closed time-like curves, essentially time loops, as long as they remain self-consistent. No paradoxes, no contradictions. You could, in theory, send information to the past, but only in ways that wouldn't create logical impossibilities. In other words, the universe might allow limited forms of time travel, provided they respect the mathematical coherence of quantum mechanics. This concept also ties into the many worlds interpretation. When a time loop occurs, reality might branch into multiple consistent timelines, avoiding paradoxes altogether. 9. Experiments hinting at quantum retrocausality. While full-blown time travel is still the realm of science fiction, there are intriguing hints that retrocausality, influence from future to past, might exist on a quantum level. Experiments using entangled photons have shown correlations that appear to be affected by choices made after the photons were emitted. These results don't necessarily prove backward causation, but they do suggest that quantum information doesn't obey classical temporal order. At the quantum scale, it seems that the future and the past are not separate. They are quantum entangled in a single reality. 10. Consciousness and temporal awareness. Now let's bring this back to the mind, to our perception of time. Neuroscience shows that the brain doesn't perceive time as a smooth flow. Instead, it samples reality in discrete chunks, about 30 to 40 frames per second. Between those frames, our brain fills in gaps, creating the illusion of continuous motion, much like a film projector. If consciousness operates in discrete moments, and if quantum physics governs the transitions between them, then our subjective experience of time may itself be a quantum process. Some researchers even propose that consciousness could access information across time through mechanisms like quantum entanglement in neural microstructures. This might explain phenomena like intuition or déjà vu, not as mysticism, but as the brain's natural sensitivity to non-linear time correlations. It's speculative, but fascinating, and it suggests that awareness may not be bound by linear time as strictly as we assume. 11. Quantum time crystals and temporal symmetry breaking. One of the most remarkable recent discoveries in quantum physics is the time crystal, a phase of matter that exhibits motion not through space, but through time. Proposed by Nobel laureate Frank Wilczek in 2012, and first realized experimentally in 2017, a time crystal is a system that repeats its state in time, like a pendulum that keeps swinging forever, but without consuming energy. It's as if the atoms remember their past configurations and echo them endlessly. Time crystals demonstrate that time can behave like a quantum dimension of structure, not just a direction of change. They could have major implications for quantum computing, stability, and, intriguingly, our understanding of temporal order in consciousness. 12. Quantum gravity and the end of classical time. At the deepest level, where quantum mechanics and general relativity meet, time may not exist at all. In quantum gravity, particularly in the Wheeler-DeWitt equation, the universe's fundamental wave function has no time variable. It describes a static, timeless reality, a vast configuration of all possible states. Physicists like Carlo Rovelli and Julian Barbour suggest that time emerges only as an approximation, a relational property between events. In this picture, there's no universal clock ticking away. Instead, what we call time is the way one part of the universe changes relative to another. Our perception of time's flow could simply be the brain's way of tracking correlations between changing quantum states. 13. The quantum now. Even though physics may describe a timeless universe, our experience insists that there is a now, that fleeting, vivid point where existence feels most real. The quantum now may be the intersection where all possibilities, past and future, collapse into a single, experienced reality. Each conscious moment could correspond to a quantum collapse, a reduction of many potential futures into one experienced present. In that sense, we're not traveling through time. Time is constantly reconstructing itself around us. Each moment is a new quantum crystallization of the universe's informational wave function. 14. Could the future already exist? If time is not linear, then perhaps the future already exists, not as a fixed destiny, but as a landscape of probabilities. We may not be able to change the entire map, but we can choose which path through it becomes real. Quantum mechanics tells us that observation shapes outcomes. So maybe consciousness is the process through which potential futures become actual experiences. This doesn't mean we're creating the future from nothing. Rather, we're selecting it from among pre-existing quantum possibilities. In this view, free will isn't abolished, it's refined. We're co-authors of a probabilistic cosmos, not prisoners of fate. 15. Closing thoughts. Time as participation. When we study quantum time, we're reminded that the universe is not a clockwork mechanism ticking blindly forward. It's a living informational system where observation, memory, and anticipation intertwine. Perhaps the reason time feels like a river is because we are the current, consciousness itself flowing through the quantum fabric of space-time, weaving potential into history. The past doesn't disappear, it simply becomes encoded information. The future doesn't wait, it's already there, shimmering as a spectrum of possible realities. And the present, this very moment, is the universe becoming aware of itself, again and again. Chapter 17. Quantum Paradox. When reality defies logic, let me take you to a quiet physics lab. It's late at night. The fluorescent lights hum softly. The air carries the smell of cooled metal and ionized dust. And on a table sits a black box surrounded by cables and mirrors. A graduate student, half awake and holding a cup of coffee, clicks a button. A single photon, a tiny packet of light, begins its journey through the apparatus. It will travel a few centimeters, bounce off a mirror, split into two possible paths, and meet again at a detector. And yet, in that tiny moment, that photon will do something that breaks every rule of logic we've ever known. Welcome to the world of quantum paradoxes, where particles can be in two places at once, causes can follow their effects, and measuring something can change what it is. 1. The double slit experiment. The origin of all paradox. Every discussion of quantum weirdness begins here, with the double slit experiment. It's deceptively simple. You fire particles, electrons, photons, even molecules at a barrier with two narrow openings. Behind it is a screen that records where they land. When both slits are open, something astonishing happens. The particles don't form two clusters, as you'd expect, but an interference pattern, a series of light and dark bands, just like ripples on a pond. Each particle behaves like a wave, interfering with itself, as if it went through both slits at once. But here's the kicker. When you place detectors to check which slit the particle actually went through, the interference pattern vanishes. Suddenly, the particle chooses one slit or the other. No more wave behavior. The act of observation seems to decide what's real. Not the particle, not the apparatus, but the measurement itself. Richard Feynman once said that this experiment contains the only mystery of quantum mechanics. And he was right. Everything else, entanglement, superposition, quantum information, grows from this paradox. 2. Schrödinger's cat, a thought experiment that refused to die. A few years after this strange behavior was discovered, Erwin Schrödinger tried to make sense of it by turning it into a story. He imagined a cat locked in a sealed box with a vial of poison, a Geiger counter, and a tiny radioactive atom. If the atom decays, the detector triggers and kills the cat. If it doesn't decay, the cat lives. According to quantum theory, before we open the box, the atom exists in a superposition, both decayed and undecayed. Therefore, the cat must also be in a superposition, both alive and dead, until observed. This was meant as a critique, a way of showing how absurd the idea of quantum superposition seems when applied to macroscopic things. But instead of killing the idea, Schrödinger's cat became a symbol of quantum mystery itself. Because, as absurd as it sounds, the mathematics still works. Until observation, reality truly exists as a probability wave, not a definite outcome. 3. The quantum measurement problem. So why does the wave function collapse when we measure it? That question, the measurement problem, remains one of the deepest puzzles in physics. According to the equations, every quantum system evolves smoothly and deterministically. There's no sudden jump, no collapse. But when we measure, reality seems to choose one outcome and discard the rest. This raises profound questions though. Mumio, does observation actually create reality? Is consciousness necessary for measurement? Or is the collapse just an illusion, a convenient simplification? Different interpretations of quantum mechanics offer different answers, and each comes with its own paradoxes. 4. The many worlds. Interpretation. Nothing collapses. In 1957, Hugh Everett III proposed a radical idea. What if the wave function never collapses at all? What if instead all possible outcomes occur, but in different parallel branches of the universe? When you measure an electron's spin, you see it up, while in another branch of reality, a version of you sees it down. Every quantum event splits the universe into countless copies, a vast branching tree of possibilities. In this view, Schrödinger's cat is never really dead or alive. Both outcomes exist, but in different worlds. Nothing collapses, reality simply expands. The many worlds interpretation elegantly removes the mystery of collapse, but it introduces new ones. Where are these worlds? Can they interact? And if everything possible happens, what does probability even mean? It's logically consistent and deeply unsettling. Even today, physicists are divided between admiration and discomfort for Everett's idea. 5. The quantum eraser, erasing the past. In 1999, physicists at the University of Maryland took the double-slit experiment a step further. They created the delayed choice quantum eraser, a version that seems to rewrite the past. Here's how it works. Photons are sent through a double slit, creating interference patterns. But after the photon has already gone through the slits, a secondary system can erase or restore the which path information. If the path information is erased, even after detection, the interference pattern reappears. If it's preserved, it disappears. The results suggest that future measurements can influence past events, as though the universe retroactively decides what the photon did based on what we choose to observe later. Physicist Yoon-Ho Kim, who led the experiment, said it best. It's as if the photon knows in advance how it will be measured. But of course it doesn't know. The paradox arises because our classical idea of time, cause followed by effect, doesn't apply to quantum systems. What's happening isn't a signal from the future, but a deep entanglement between measurement and reality that transcends linear time. 6. The quantum Zeno effect, freezing time with observation. Another paradox: watching something can stop it from changing. The quantum Zeno effect, named after Zeno's ancient paradox of motion, describes how repeated observation can freeze a quantum system in its state. Imagine an unstable atom that could decay at any moment. If you measure it continuously, observing its state again and again, you can actually prevent it from decaying. Observation holds it in place. It's as if the act of measurement locks the wave function, forcing the universe to stay in the same configuration. This effect has been confirmed experimentally, even used in quantum computing to maintain coherence. But philosophically, it's profound. The mere act of attention seems to stabilize reality. What does that say about consciousness? And could it be that awareness, or observation itself, plays a creative role in the unfolding of the universe? 7. The quantum Cheshire cat, properties without the object. In 2014, researchers at the Neutron Science Laboratory in Japan created a strange new paradox inspired by Lewis Carroll's Cheshire cat. They sent neutrons through an interferometer, separating the particles' physical paths from their magnetic properties. Astonishingly, they found that the neutron and its magnetic moment appeared to travel along different paths. In other words, a particle's property, like its spin, can be found in one place while the particle itself is elsewhere. It's like seeing the grin of the Cheshire cat floating in midair long after the cat itself has disappeared. What this means, in quantum terms, is that objects and their properties aren't inseparable. Reality isn't made of solid things, but of relational information, a network of probabilities linking what we measure to how we measure it. 8. Wigner's friend. Who collapses the wave function? Imagine this. You're inside a sealed laboratory, performing a quantum experiment. You measure a particle, and to you, the result is definite. The wave function has collapsed. But to an observer outside the lab, you and the particle are still in superposition, a mixed, entangled state. This is Wigner's friend, a thought experiment proposed by Eugene Wigner in 1961. It shows that the boundary between observer and system is ambiguous. If consciousness causes collapse, then whose consciousness counts? Recent experiments like the 2019 study at Heriot-Watt University in Scotland have simulated versions of Wigner's friend using entangled photons. The results were stunning. They suggest that two observers can experience conflicting realities, and both can be correct within their own frames of reference. Reality, it seems, might not be absolute, but observer-dependent. 9. Contextuality, the end of classical logic. Classical logic tells us that things have definite properties whether or not we look at them. A ball is red or it isn't. A door is open or closed. Quantum physics breaks that assumption. Contextuality means that the properties of a quantum system don't exist independently of the measurement context. What you find depends on how you look. In 2019, experiments with trapped ions confirmed that contextuality is a fundamental feature of reality, not just a glitch in our understanding. It's built into the mathematics of quantum mechanics. That's what makes quantum paradoxes so powerful. They aren't mistakes. They're windows into how the universe truly works, beyond classical categories of true and false. 10. When paradoxes become principles. Over time, what began as absurd contradictions have become the foundations of technology. Superposition, enables quantum computers to perform vast computations in parallel. Entanglement forms the backbone of quantum cryptography and teleportation. Decoherence explains how quantum behavior gives rise to the classical world. Paradoxes aren't failures of understanding, they're guideposts to deeper truth. They show us where our intuition, built for everyday life, collides with the underlying logic of the cosmos. 11. Quantum logic, the universe's different kind of reasoning. In classical logic, something can't be both true and false. In quantum logic, it can be both, in superposition. Think of Schrödinger's cat again. It's not alive or dead until observed, but the quantum description isn't either or. It's and, alive and dead, until measurement collapses the duality into one. This doesn't mean quantum mechanics is irrational, it's transrational. It operates on a higher logical structure where truth values are not binary, but probabilistic amplitudes. Reality, in this view, isn't made of facts, it's made of potentialities. 12. The human side of the paradox. Every paradox in quantum mechanics reflects a paradox in ourselves. We want the universe to make sense, to be predictable, logical, governed by cause and effect. But quantum physics shows that, at the deepest level, reality is participatory. We can't stand outside it, we're part of it. When we measure, we influence. When we observe, we define. Even our act of questioning shapes what answers can exist. That's not mystical, it's empirical. Every experiment we've discussed, from double slits to delayed choice, supports this participatory framework. So perhaps the ultimate paradox is that, by studying the universe, we're also studying the mechanism by which it becomes real. 13. Closing reflections. Living with the paradox. If quantum physics teaches us anything, it's humility. We inhabit a universe far stranger than any story we could invent. And yet, it works. Your smartphone, your GPS, your MRI scanner all rely on principles that once seemed paradoxical. The weirdness is not just academic, it's the foundation of modern reality. The paradoxes aren't there to confuse us. They remind us that logic is a tool, not a boundary, and that mystery is not the absence of understanding, but the beginning of it. The quantum world doesn't ask us to abandon reason. It invites us to expand it, to include possibilities that classical logic never imagined. And so the calm professor concludes, in the quantum realm, paradox is not a problem. It's the signature of truth. Chapter 18. Quantum information, the universe as a computer. Imagine for a moment that everything you see, the stars, the galaxies, your thoughts, your dreams, is not built from matter, but from information. Not the kind of information you find in a book or a web page, but quantum information, the smallest possible unit of knowledge about the universe, encoded in qubits instead of bits, in probabilities instead of certainties. It's a bold thought, one that would make both philosophers and physicists pause. But in the last few decades, science has quietly begun to consider this possibility in earnest. That the universe at its deepest level may not be a grand machine of gears and forces, but rather a vast computation, a cosmic algorithm continuously running, updating, evolving. Let's rewind to where this idea began. The birth of quantum information in the mid-20th century, when computers were still massive, clunky machines filling entire rooms, a few visionaries began to think about the nature of information itself. Claude Shannon, the father of information theory, showed that any signal, no matter how complex, could be reduced to a binary code, a series of ones and zeros. Information could be measured, transmitted, stored, and, most importantly, quantified. But physics was still in another realm, dealing with particles and waves, energy and matter. That is, until one scientist asked a seemingly simple question: what happens to information when a physical system changes? This question would eventually tie physics and information together in ways no one could have predicted. John Archibald Wheeler, one of the most creative physicists of the 20th century, and a mentor to Richard Feynman, proposed a daring idea. He called it "it from bit." According to Wheeler, the physical world arises from the answers to yes or no questions, from the binary nature of measurement itself. In other words, information doesn't describe reality. Information creates reality. That was the seed of quantum information theory, the realization that every particle, every wave, every field could be understood not as a solid object, but as data, quantum data. Qubits, the language of reality. In classical computing, a bit can be either 0 or 1, simple but limited. A quantum bit, or qubit, on the other hand, can be both 0 and 1 at the same time, through a property known as superposition. When measured, it collapses into one of those two outcomes. But until then, it carries a cloud of probabilities. Now imagine a computer built not from transistors, but from qubits, a quantum computer. Instead of calculating one path at a time, it explores all possible paths at once, like a spider casting a web across reality. This isn't theoretical anymore. Companies like IBM, Google, and D-Wave have already built early prototypes of quantum processors that use a handful of qubits, cooled to near absolute zero. They're fragile, so sensitive that even a stray vibration or a flicker of heat can destroy their quantum state. But when stable, they do something extraordinary. They calculate in parallel across dimensions of probability. Quantum computing isn't just a faster kind of classical computing, it's a different language, one that seems to mirror how the universe itself might process information. Entanglement, nature's networking system. But where does all this information go? How does the universe keep track of it? The answer lies in one of the most mysterious aspects of quantum mechanics, entanglement. When two particles become entangled, their quantum states are linked, no matter how far apart they are. Change one and the other responds instantaneously, even across galaxies. Einstein famously called this spooky action at a distance. Today, it's not just accepted, it's measurable. Experiments using photons sent between satellites and ground stations have demonstrated entanglement over hundreds of kilometers. And soon, quantum physicists plan to expand this into a quantum internet, a global network of entangled systems, transmitting information not through energy, but through correlation. In this network, information doesn't travel. It simply exists, everywhere at once, distributed across a web of quantum relationships. And in that sense, the universe begins to look less like a machine and more like a vast computational network, an interconnected field of quantum data. Black holes, the great information paradox. This brings us to one of the greatest mysteries in physics, and perhaps the most important test of whether the universe truly behaves like an information processor. In the 1970s, Stephen Hawking discovered that black holes aren't entirely black. They emit a faint radiation, now known as Hawking radiation, due to quantum effects near their event horizons. But this discovery led to a paradox. If black holes evaporate over time, what happens to the information about everything that fell into them? According to quantum mechanics, information can never be destroyed. According to general relativity, it can. The clash between those two principles has haunted physics ever since. But in the past 2 decades, a new idea emerged. Perhaps the information isn't lost at all. It's encoded on the surface of the black hole, like data stored on a holographic disk. This is the holographic principle, proposed by physicist Gerard T. Hooft and expanded by Leonard Susskind. It suggests that the 3-dimensional universe we experience might actually be a projection, all the information describing it encoded on a 2-dimensional boundary. If that's true, then the universe is not just like a computer. It is a cosmic quantum computer projecting the illusion of space and matter from deeper informational laws. The experiments testing the universe's code. For decades, the notion that the universe might process information was purely theoretical, a fascinating, almost mystical metaphor. But over the last 30 years, physics has begun to test this idea. In the early 2000s, researchers at IBM began experimenting with quantum processors built on superconducting circuits. These tiny frozen loops of niobium metal were cooled to near absolute zero, where they behaved not like ordinary electronics, but like quantum oscillators. When scientists manipulated them using microwave pulses, they observed something incredible. They could encode information in quantum superpositions. Each circuit wasn't just on or off. It existed in a delicate dance of both possibilities. At first, the results were unstable, fleeting. The qubits would lose coherence in microseconds. But over time, advances in quantum error correction and cryogenic stability began to stretch those lifespans. Today, IBM's Eagle and Condor quantum processors boast over 1,000 operational qubits, each interconnected through carefully tuned superconducting pathways. To the scientists observing them, these machines aren't merely computers, they're laboratories for testing the structure of reality itself. The quantum internet, entanglement across the world. Meanwhile, across the world, quite literally, another revolution was brewing. In 2017, Chinese physicists launched a satellite named Mitius after an ancient philosopher who studied light and optics over 2,000 years ago. Mitius was no ordinary satellite. It was equipped with one of the most advanced quantum communication systems ever built. From orbit, Mitius fired pairs of entangled photons toward two distant ground stations, one in Beijing, the other in Vienna, separated by thousands of kilometers. And yet, when scientists measured those photons, their results were correlated instantly. It was the largest scale demonstration of quantum entanglement in human history. This was not just a physics experiment. It was the birth of the quantum internet, a global network where information is shared not through traditional data streams, but through quantum correlations. Unlike classical data, which can be intercepted, copied, or altered, quantum information is self-protecting. If anyone tries to observe or intercept it, its state collapses, revealing the intrusion immediately. That's why quantum encryption is often described as unhackable. It's not that humans haven't found a key, it's that the lock itself vanishes the moment you try to touch it. The implications for security, communication, and even consciousness studies are profound. For the first time, humans have begun to build systems that operate under the same informational laws that may govern the universe itself. The holographic universe, information as geometry. But the most breathtaking implications don't come from technology, they come from cosmology. When physicists first encountered the black hole information paradox, many believed the question was purely academic, something that would never affect real-world observations. But then, in 1997, a young physicist named Juan Maldacena proposed an idea that would ripple across the entire landscape of modern physics. He suggested that a particular kind of universe, one described by quantum field theory, could be exactly equivalent to a universe described by gravity in higher dimensions. This idea became known as the ADS/CFT correspondence, or more simply, the holographic principle. It meant that what we perceive as a three-dimensional universe might be a projection of quantum information stored on a lower dimensional boundary, like a cosmic hard drive. Every particle, every galaxy, every thought could, in theory, be encoded in this vast informational structure. Space itself might emerge from entanglement, geometry arising from pure data. recent experiments using quantum simulators have attempted to model this holographic structure. Physicists have used entangled atoms and trapped ions to recreate miniature universes where geometry emerges from patterns of quantum information. In other words, we are beginning to see the blueprints of reality's code, not metaphorically, but physically on the lab bench. Quantum teleportation, moving information, not matter. If information truly lies at the heart of reality, then perhaps it can be transferred without moving matter at all. This is not science fiction, it's quantum teleportation, and it has already been achieved. In 2020, researchers at Fermilab and Caltech teleported quantum information between two nodes over 44 kilometers of fiber optic cable. No particles were transported, no signals traveled faster than light. Instead, through the phenomenon of entanglement, the state itself, the information describing one particle was perfectly recreated in another. To many, this was a practical milestone for quantum communication, but philosophically, it's staggering. It implies that identity, state, and information can exist independently of their physical medium. The thing doesn't need to move, its information does. And in a universe governed by information, that may be the only thing that truly matters. Is the universe a simulation? Naturally, such ideas have reignited one of the most provocative modern debates. Are we living inside a simulation? Physicists and philosophers like Nick Bostrom and Max Tegmark have argued that if information is the fundamental substrate of reality, and if consciousness and computation can exist on that substrate, then our universe might simply be one of many simulated realities within a cosmic hierarchy. But others, like theoretical physicist Sabine Hossenfelder, warn that such arguments are more metaphysical than scientific. If everything we can observe follows the same physical laws, then the distinction between real and simulated may be meaningless. After all, if the universe computes itself perfectly, how could we ever tell the difference? Still, experiments are quietly probing the boundaries. At the Fermi National Accelerator Laboratory, researchers are looking for subtle pixelation in space-time, a kind of quantum graininess that might reveal whether reality is truly continuous or fundamentally discrete. So far, no evidence has been found, but even if the simulation idea remains unproven, its questions have value. They remind us to look deeper, not at what we see, but at the rules behind seeing. Consciousness and quantum information. Now we reach one of the most delicate frontiers of all, the relationship between mind and information. If the universe processes information, could consciousness be part of that process? Could awareness itself arise from quantum phenomena, from the brain acting as a quantum information processor? The idea has been both celebrated and criticized. Physicist Roger Penrose and anesthesiologist Stuart Hameroff proposed that quantum effects within microtubules, the structural scaffolding of neurons, might play a role in producing consciousness. They called it the OR theory, short for orchestrated objective reduction. In their view, consciousness doesn't just observe quantum collapse, it is quantum collapse. Each moment of awareness corresponds to the resolution of a quantum state, creating the flow of experience we call mind. Skeptics, however, argue that the brain is far too warm and chaotic for delicate quantum coherence to survive. Yet recent findings in quantum biology, such as quantum tunneling in enzymes and quantum coherence in photosynthesis, suggest that life, somehow, does harness quantum effects, even in warm, noisy environments. So the possibility remains open. Perhaps consciousness and quantum information are two sides of the same cosmic coin, one subjective, one objective, entangled across the divide between matter and meaning. The final code, information never dies. And finally, we return to the question that started it all. What happens to information when it disappears? Everywhere scientists look, the answer seems to be the same. It doesn't. When energy transforms, when matter decays, when black holes evaporate, the information persists, encoded somewhere, somehow. Like a cosmic accountant, the universe keeps perfect balance sheets. Nothing is lost, only transformed. And if information is eternal, if every quantum event leaves an indelible mark, then perhaps our own consciousness too is part of that unending computation. Maybe we are not observers of the universe's code. Maybe we are lines of it, patterns in the grand algorithm of existence, forever looping, evolving, and expressing new combinations. So the next time you close your eyes and feel that quiet awareness, that flicker of being, remember, somewhere deep in the quantum substrate of reality, the universe might be processing you as both question and answer. Because in the end, as John Wheeler said, it from bit, reality arises from the answers the universe gives to its own questions. Spoken goodbye. And now we arrive at the edge of knowing, at the soft horizon where science fades and silence begins to speak. You've journeyed through the folds of quantum mystery, and maybe, somewhere between thought and sleep, you've felt a quiet recognition. If this voyage resonated with you, leave a trace, a comment, a like, a reflection, each one a small signal rippling through the field of shared wonder. Subscribe to Sleep Entangled for more stories, where knowledge drifts into dream and curiosity becomes calm. Until we meet again, rest deeply, think softly, and let your awareness entangle gently with the cosmos itself.